Have you ever noticed how quickly we underestimate people who lived thousands of years ago? We picture ancient civilizations as societies struggling with primitive tools, limited knowledge, and impossible obstacles. Then we stand in front of something like the Great Pyramid of Giza, and that picture begins to fall apart. The first thing that surprises most visitors isn't the age of the pyramid, it's the scale. Each limestone block is large enough to make you wonder how anyone could possibly move it. Then you remember there are more than 2 million of them. Suddenly, the question isn't simply, how was this built? It's, how was this even organized? That question becomes even more interesting when you realize Egypt isn't unique. Across Peru, enormous stones were shaped so precisely that some joints remain difficult to slide a blade between. In Lebanon, builders positioned blocks weighing hundreds of tons. In India, an entire temple emerged from a single mountain. The Romans created concrete that still puzzles material scientists, while Greek architects designed theaters that could carry a human voice without electricity. At first glance, these places seem completely unrelated. Different continents, different cultures, different languages, different beliefs. Yet they all point toward the same conclusion. Ancient builders weren't solving the same problem. They were solving different problems using the same approach. They observed carefully. That's a detail I think we often overlook. Today, when we face a difficult engineering challenge, our instinct is usually to ask what new technology can solve it. Ancient engineers had no such luxury. If something didn't work, they couldn't wait for a better machine to be invented. They had to understand the world that already existed around them. They watched rivers, they studied stone, they paid attention to gravity. They learned how different materials behaved over time. Most importantly, they remembered what worked. Generation after generation, small discoveries accumulated until they became knowledge sophisticated enough to build structures that still dominate landscapes thousands of years later. Perhaps that's why these monuments continue to fascinate us, not because they prove ancient people possessed mysterious powers, but because they remind us that intelligence doesn't always arrive with modern technology. Sometimes it begins with a careful observation that almost everyone else ignores. That becomes remarkably clear in Egypt. For centuries, the pyramids have inspired theories ranging from brilliant engineering to impossible speculation. But archaeology paints a picture that's both simpler and, in many ways, far more impressive. Ancient Egypt possessed one extraordinary advantage before construction even began: the Nile. To most people, it was a river. To ancient engineers, it was infrastructure. Every year, its waters connected distant quarries, workshops, and cities across the kingdom. Recent archaeological research suggests waterways and canals reached much closer to pyramid construction sites than historians once believed. That meant many of the heaviest stones probably spent much of their journey floating rather than scraping across dry desert. That single decision changes everything. Transporting several tons across water is difficult. Transporting the same weight entirely across sand is something else entirely. Good engineering often starts by asking a simple question: am I solving the right problem? The Egyptians rarely fought nature if they could persuade nature to help instead. The same thinking appeared inside the quarries themselves. Without hardened steel, workers carefully cut channels around limestone blocks before driving dry wooden wedges into narrow cracks. Once soaked with water, the wood slowly expanded. The pressure increased little by little until sections of stone finally separated from the bedrock. There's nothing dramatic about that process. It doesn't happen in seconds. No sparks, no explosions, just patience. Modern life has conditioned us to expect instant results. Ancient construction almost teaches the opposite lesson. Some projects weren't designed around months. They were designed around decades. Perhaps patience wasn't simply a virtue, it was part of the technology. Then came another challenge: moving the finished blocks across land. One small painting discovered inside an Egyptian tomb has become surprisingly important. It shows workers pulling an enormous stone statue on a wooden sled, while another person pours water onto the sand directly in front of it. For a long time, that detail received little attention. Today, experiments suggest damp sand can reduce friction enough to make heavy loads significantly easier to pull. I find that fascinating. The breakthrough wasn't hidden inside an extraordinary machine. It was hidden inside an ordinary observation. Someone noticed wet sand behaved differently from dry sand. That simple idea, repeated thousands of times across years of construction, may have created one of humanity's greatest monuments. And once you begin seeing ancient engineering through that lens, another realization quietly appears. The pyramids weren't built because ancient people ignored the laws of physics. They were built because they understood them better than we often give them credit for. The question is, what happens when your greatest challenge isn't moving stone across sand? It's building on land that never stops moving. High in the Andes Mountains, nearly 13,000 feet above sea level, sits a place that often leaves first-time visitors confused. This is Puma Punku. Unlike the pyramids, it doesn't overwhelm you with height. There are no towering monuments visible from miles across the landscape. Instead, enormous stone blocks lie scattered across a windswept plateau, almost as though a giant construction project was suddenly interrupted. At first glance, it feels unfinished. Then you begin looking more closely. The surfaces are remarkably flat. Corners meet at sharp angles. Grooves run through the stone with surprising consistency. Some blocks appear to fit together with a level of precision that has fueled speculation for decades. It's tempting to assume the mystery lies in the tools. In reality, the mystery may lie somewhere much simpler: the environment. One thing I've always found interesting about ancient engineering is that every civilization seems to reflect the landscape it grew from. Egypt learned from rivers. The Andes learned from earthquakes. That's an entirely different teacher. This region lies within one of the most active seismic zones on Earth. Buildings that appear solid can fail in seconds once the ground begins to move. Under those conditions, strength alone isn't enough. The structures need flexibility. Archaeologists studying Andean construction have found that many ancient builders shaped individual stones so they locked together with extraordinary precision instead of relying entirely on thick layers of mortar. During seismic movement, these carefully fitted blocks could shift slightly and redistribute stress without immediately collapsing. It's a remarkably elegant idea. Rather than trying to stop nature, the builders allowed the structure to move with it. There's something surprisingly modern about that philosophy. Today, engineers designing skyscrapers in earthquake-prone regions often follow the same principle. The goal isn't to create a building that never moves. The goal is to create one that survives movement. Different technology, the same way of thinking. Perhaps that's one of the biggest lessons hidden inside places like Puma Punku. Innovation isn't always about inventing something completely new. Sometimes it's about understanding your environment more deeply than anyone before you. That perspective makes the site feel less mysterious, not because the achievement becomes ordinary, but because it becomes understandable. And somehow, that's even more impressive. If Puma Punku teaches us how ancient builders responded to an unstable landscape, our next destination asks a very different question. How do you move something so heavy that your brain almost refuses to believe the number? That question leads us to Baalbek. In modern-day Lebanon stands some of the largest stone blocks ever incorporated into an ancient construction project. One unfinished block still resting in the nearby quarry is estimated to weigh more than 1,000 tons. Numbers like that are strangely deceptive. You can read them, you can repeat them, but until you're standing beside the stone itself, it's almost impossible to appreciate what they actually mean. Perhaps that's why Baalbek has inspired so many impossible explanations over the centuries. Our instincts often tell us that if something looks impossible, it must have required impossible technology. History rarely works that way. Ancient builders almost certainly didn't attempt to lift a 1,000-ton block into the air in one dramatic moment. Engineering usually isn't dramatic. It's incremental. Researchers believe projects like Baalbek relied on combinations of prepared ramps, sledges, rollers, levers, and careful coordination, allowing builders to divide one overwhelming challenge into hundreds of manageable ones. That idea feels surprisingly familiar.
Whether you're building a bridge, writing software, or solving a scientific problem, the principle hardly changes. Large problems become approachable when they're broken into smaller decisions. Looking at Baalbek today, it's easy to admire the finished stones, but I sometimes wonder if the real masterpiece wasn't the construction itself. It was the planning. Someone had to calculate where every block would travel. Someone had to organize hundreds of workers. Someone had to make thousands of small decisions that nobody would remember once the monument was complete. That's often the invisible side of engineering. When everything works perfectly, all anyone notices is the result. The planning disappears. The builders disappear. Only the stones remain. And in India, those stones will soon become something even more extraordinary. Not a wall, not a platform, an entire mountain transformed into architecture.
The Kailasa Temple in western India begins with an idea so unusual that it's easy to miss just how radical it really was. Most buildings start with empty ground. Materials are gathered, foundations are laid, walls slowly rise. Kailasa followed none of those rules. Instead of bringing stone to the monument, the builders revealed the monument from the stone that was already there. Everything you see today, the towering sanctuary, the courtyards, bridges, stairways, carved elephants, pillars, and shrines, once existed as part of a single mountain. Nothing was assembled. Everything was uncovered. I've always found that difference fascinating. Building something requires imagination. Removing everything that doesn't belong requires an entirely different kind of confidence. Researchers believe construction began from the very top of the rock and gradually moved downward. At first, that seems counterintuitive. Why not start at the base like almost every other structure? Then the logic becomes obvious. Working from above meant the mountain itself acted as permanent scaffolding. As workers carved deeper, gravity carried broken rock downward instead of forcing builders to lift enormous amounts of debris back uphill. Sometimes the smartest engineering solution isn't adding another tool, it's allowing gravity to do part of the work. That idea feels surprisingly timeless. The best engineers rarely defeat nature. They persuade nature to work alongside them. Of course, this approach came with an extraordinary challenge. There was almost no room for error. If a wall was carved too deeply, another block couldn't simply be brought in to replace it. If an important column fractured, the mountain couldn't be reset. Every decision permanently changed the final result. Try imagining that kind of responsibility. Even carving a small piece of wood requires concentration because every cut removes something forever. Now imagine making those decisions inside an entire mountain. Researchers estimate that hundreds of thousands of tons of basalt were removed during the creation of Kailasa. That's an astonishing amount of stone. But I don't think the quantity is what deserves the most admiration. The planning does. Someone had to imagine the completed temple while it was still hidden inside solid rock. Someone had to know which stone should remain and which stone needed to disappear. Perhaps that's the true masterpiece. Not carving, visualization, seeing something that didn't yet exist. By the time visitors stand inside Kailasa today, they rarely think about the millions of individual hammer strikes that made the temple possible. Like so many great engineering achievements, the effort becomes invisible once the work is complete. Around the same period that master builders in India were carving mountains into architecture, another civilization was experimenting with something much smaller. At least it seemed smaller. It wasn't another monument. It wasn't another machine. It was a building material. And thousands of years later, scientists are still trying to understand exactly why it works so well. When most people picture Roman engineering, they think of long aqueducts crossing valleys, perfectly straight roads, or enormous amphitheaters filled with thousands of spectators. Yet none of those structures could have survived without something far less dramatic: concrete. That sounds ordinary today because concrete surrounds us. It's beneath our streets, inside our homes, holding up our bridges.
But Roman concrete wasn't the same material we pour today. One of its most important ingredients came from volcanic ash. For years, researchers studying ancient Roman harbors noticed something unexpected. Some of these structures had remained exposed to waves and salt water for nearly 2,000 years, yet parts of the concrete appeared to have grown stronger instead of weaker. That observation challenged a basic assumption. We often think age automatically means deterioration. Roman concrete reminds us that nature doesn't always behave the way we expect. Scientists now believe seawater slowly triggered chemical reactions inside the concrete, producing new minerals that reinforced tiny cracks over time. In other words, the sea wasn't simply attacking the structure. In some cases, it was helping preserve it. There's something quietly humbling about that. We like to imagine history as one continuous line of progress, where every generation improves on the last. Reality is far more complicated. Sometimes knowledge moves forward, sometimes it's forgotten, and occasionally the past still has something to teach the future. That lesson becomes even more remarkable when we leave Roman harbors behind and travel to Greece, where ancient engineers mastered something that cannot be held in your hands: sound itself.
Unlike the pyramids or Kailasa, the Theater of Epidaurus doesn't impress you by moving enormous stones. Its greatest achievement is almost invisible. You only notice it when someone begins to speak. Imagine sitting in the highest row of a theater carved into a Greek hillside. The stage is hundreds of feet away. There are no speakers hidden beneath the seats, no microphones, no electronics quietly amplifying every word. Yet a performer standing at the center can still be heard with remarkable clarity. 2,000 years ago, that wasn't entertainment. It was engineering. The builders didn't understand sound through computer simulations or mathematical software. They understood it through observation. Over generations, they experimented with slopes, seating angles, stone surfaces and proportions, gradually discovering which designs carried the human voice most effectively. Researchers have suggested that the limestone seating helps reduce certain low-frequency background sounds while reflecting the frequencies most important for speech. Whether every detail was planned from the beginning or refined slowly through experience is still debated. But perhaps that's the wrong question, because regardless of how they arrived, they arrived. That's what engineering often looks like. Progress doesn't always happen because someone suddenly becomes a genius. More often, it happens because countless small improvements accumulate until the final result feels almost effortless. I think that's why the Theater of Epidaurus feels different from many modern buildings.